Thin layer chromatography, or TLC, is a chromatographic method used to separate mixtures of non-volatile compounds, commonly used in organic chemistry. TLC is performed on a glass or plastic-backed plate. A baseline is marked on the plate, along with labels. The mixture being examined, and reference compounds, are dissolved in an appropriate solvent and applied near the bottom edge of the TLC plate in small spots. The plate is placed in a jar, and the solvent, the mobile phase, separates the mixture based on physical properties of each component. Despite the fact that more instrument-heavy separation techniques have more resolving power than TLC, it is the speed and low cost that makes TLC an attractive technique for on-the-fly qualitative analysis. This video will demonstrate the preparation, operation, and analysis of thin-layer chromatography. Chromatographic techniques include a stationary and mobile phase. In TLC, the stationary phase consists of a thin layer of material fixed to the plate. The material is a polar substance, such as silica gel. The mobile phase is a non-polar liquid that moves up the absorbent layer by capillary action. As the mobile phase moves up the plate, it drags along the components of each spot, which are subsequently separated based on polarity. Compounds that are less polar will spend more time in the mobile phase as it is pulled up the plate. Compounds that are more polar are more attracted to the stationary phase, and will therefore not move up the plate as far. The separation takes place in a developing container. These can be jars with lids or beakers covered with aluminum foil. Use the smallest container available that will accommodate the TLC plate to speed up the separation. The mobile phase, or developing solvent, should be as non-polar as possible for a good separation. Shown here is an allotropic series for silica gel, a list of common mobile phases in order of increasing extracting power. A number of mobile phases can be tested simultaneously. On a clean plate, spot the dissolved sample multiple times, at least 2 centimeters apart. Apply enough mobile phase to each spot to form a circle 1 to 2 centimeters in diameter. Mark the distance the mobile phase travels. If the mobile phase is not polar enough, the sample will remain close to the initial spot. If the mobile phase is too polar, all of the sample will migrate with the solvent front. An appropriate mobile phase will show well-separated rings, with the outermost ring about 50% of the distance to the solvent front. If necessary, 2 miscible mobile phases can be mixed in varying proportions to obtain the desired properties. Here, a 1-to-1 mixture of ethyl acetate and hexane was too polar, but a 1-to-20 mixture was appropriately separated. With the mobile phase chosen, you're ready to start developing the plate. To begin the procedure, cut a commercially available TLC plate to the desired size. If the plate has a glass backing, score it with a glass cutter and carefully break along the line. With a pencil, mark a baseline about 1 centimeter from the bottom of the plate. Mark the location where the samples will be spotted along the line. Be sure the spots are at least 1 centimeter from the edge and 3 millimeters apart. Label them appropriately. Solid samples must be dissolved in a suitable solvent. Common solvents include hexanes, ethyl acetate, or dichloromethane. Use the least polar solvent that will dissolve the sample. Draw up the sample solvent mixture with a glass capillary. Gently touch the tip to the desired location on the TLC plate and remove it immediately. It is important to not disturb the stationary phase. Keep the spot as small as possible, as this leads to a better separation. If more sample is needed, spots may be applied successively at each location. Allow the solvent to dry between applications. A stream of air can be used to dry less volatile solvents. Place a piece of filter paper in the bottom of the jar to increase the vapor pressure. Add the mobile phase to a depth that does not reach the baseline. Cap the jar when not in use, so the solvent vapors do not escape. Carefully place the spotted TLC plate in the developing jar. Make sure the mobile phase is below the baseline. Watch the progress of the solvent front, the leading edge of the mobile phase, as it will move quickly up the plate. Do not allow the mobile phase to reach the top edge of the plate, as sample bands will begin to expand via diffusion. Once the solvent front nears the top, remove the plate from the developing chamber and mark the solvent front with a pencil before the solvent dries. If the compounds are not colored, a UV lamp can be used to visualize the spots. The compound will block the background fluorescence of the plate. Set the lamp to the shortwave setting and illuminate the dry plate. Using a pencil, outline any spots visible under the lamp. Another possible visualization technique is to use potassium permanganate, an oxidizing agent. Using tweezers, dip the plate into the permanganate stain. Remove and dab away excess solution with a paper towel. In a fume hood, carefully heat the plate with a heat gun to visualize the spots. Use a pencil to mark any spots that appear. Once the spots have been visualized, the substance of interest can be compared to standards, as shown here. In this example, the unknown is 1,3-diphenylpropanone, a building block in organic synthesis. By comparing the band to a known standard and benzoyl chloride, one of the starting materials, the product can be identified. The retardation factor, or RF, is used to identify the unknown compound. The RF is the ratio of the distance a compound travels up a TLC plate to the distance the mobile phase travels. The factor is determined by measuring the distance from the baseline to the spot and dividing by the distance from the baseline to the solvent front. The RF of a given component is dependent on the conditions used in the experiment, including solvent choice, thickness and activity of the absorbent, temperature, and sample size. Care should be taken to keep these factors consistent between experiments. There are several applications of thin layer chromatography. In this example, the triacylglyceride content of bat sebaceous glands was studied. The lipid surface fraction was first separated by polarity on a TLC plate. The triacylglyceride band was then removed from the plate with a spatula. The silica powder was transferred to a microcentrifuge tube with solvent. After centrifugation, the stationary phase was left at the bottom of the tube, while the compounds remained dissolved in the solvent. The triacylglycerides were then further separated by another physical property. In this case, the second dimension of separation was molecular size. TLC can also be used to monitor the progression of a chemical reaction. In this example, the starting material of the reaction was used as a standard and ran alongside the reaction solution on a TLC plate. This process was repeated at specific intervals over the course of the reaction. As the reaction progressed, the starting material band diminished and the product band enlarged. When there was no change in bands, or all of the starting material was consumed, the reaction was complete. Finally, TLC plates can be used in bioassays. In this example, compounds were separated from red clover with TLC. Each band was then placed on bacteria growing on agar plates. Molecules that showed inhibited bacterial growth were further analyzed for their antimicrobial properties. You've just watched Job's Introduction to Thin Layer Chromatography. You should now understand the underlying theory of the separation, how to choose an appropriate mobile phase for your experiments, and how to set up and operate a TLC plate. Thanks for watching.